Groves. This is the second part of the video that I'm doing on 9.1, which is basically covering power. The first part of the video was going over a review of type 1 and type 2 errors. And now I'm going to discuss understanding power using a simulation. So I've simplified these because we don't have time to go through and do the simulation. But there is a simulator that we could go through and use. And it's really kind of fun and interesting. But I think you'll get the gist of what's going on by just understanding me walking you through these problems here. Okay, so we're going to take the example that we were just doing before, okay, where we had the null hypothesis was P equals 0.63, and the alternative hypothesis is P is less than or equal to 0.63. And really what's happening here is we have two things going on. We have our null hypothesis and we have our alternative hypothesis. And so if we do the graph of the null hypothesis, okay, this area here, and we are setting alpha equal to 0.10. So we set alpha. And we gathered our evidence. And we got P hat is equal to 0.53. So for our null hypothesis, P is 0.63. And we have set alpha to be 0.10. Well, what are the values for beta and for power? Well, it's based on the graph of the alternative hypothesis. So if we were to do simulations, and we were to do simulations of size 250, what would happen as a result of that is that we would see that we know that there's an inverse relationship between alpha and beta. So if type 1 error is 0.10, and we use sample sizes of 250, and we did that many times, we would get a beta of about 3%, 0.03. And the power would be 0.97. Okay, so you can see here they have an inverse relationship, and you're going to see that power and alpha are going to go in the same direction. So what happens if we reduce the significance level from 0.10 to 0.01? To reduce the probability of a type 1 error and avoid the possibility of unnecessarily paying an extra employee, the manager reduced the significance level. And you can do that as a researcher. We can reduce the significance level to 0.01. And here's our alpha. We do simulation, and we notice now that beta is 0.19, and we notice that our power is 0.81. So we have, the conclusion is that if we take alpha, okay, if we take alpha and we reduced alpha from 0.10 to 0.01, then we can see that beta went up because there's an inverse relationship between alpha and beta. Okay, so here is our null hypothesis, the graph of our null hypothesis, and here's the graph of our alternative hypothesis. Okay. And so alpha went down, beta went up, and we notice that what happens with power from here to here, power goes down. Right? So going back to my neat notes, okay, it's important to understand the relationship between alpha and beta. They have an inverse relationship. Okay. So here we decreased the alpha, and what happened as a result of that was beta increased. And alpha and power go in the same direction. So you'll notice that in this case we reduced alpha. As a result, the power was reduced from 0.97 to 0.81. And I think seeing this visually is really nice to understand these concepts and where they're coming from. Okay, so what's going to happen next? Let's kind of focus on here. So now the manager decides that he doesn't want to sample 250 people. He wants to sample 100. And he went back to his original significance level of 0.10. So you'll notice here that we have our null hypothesis, we have our alternative hypothesis. We still have the same population parameter, 0.63 for our null hypothesis. Here, our alternative hypothesis is based on our sample statistic for p-hat 0.53. So we took n from 250 and we went to 100. All right. So when that happens, okay, what happens to power? Okay, and here alpha is equal to 0.10. Alpha is the same. Power went from 250, excuse me, the sample size went from 250 to 100. And what did you notice before? When the sample size was 250, the power was equal to 0.97. Now what happens to power, okay, when we reduce the sample size? And notice that power now goes down and it is 0.76. So you can see that sample size has a huge impact on the power of the statistic. So if we decreased n, all right, we are going to have the power automatically become less. So one way to increase power, another way to increase power is to increase the sample size. Okay. So what's happening in this example? The manager takes 2 random samples of 100 customers. His first sample, he found 50 customers, okay, out of the 100, 50%, who had to wait, and we maintained alpha of 0.10. So now we still have the same null hypothesis. Okay, so our null hypothesis is P is equal to 0.63. Our alternative hypothesis is P is less than 0.63. So in this case right here, you can see that we have our null hypothesis and we have 0.5. And if we compare this power to the power that we had over here, notice that this power is 0.91. This power was 0.76. So the point that I want you to be looking at here is what's happening when we change our evidence for the alternative hypothesis. Here it's 0.53. Okay? Alpha is the same in both cases, 0.10. The sample size in both cases is 100. And I want to do another comparison. Right? So now the manager does another survey of 100. And he gets his p hat for his alternative to be 0.45. And so now what's happening? We've got p hat of 0.45, p hat of 0.50, and p hat of 0.53. So, are you seeing the relationship that's taking place as the p hat gets further away from our null hypothesis? The power increases. Okay, so here p hat's 0.53, the power is 0.76. Here p hat's 0.50, the power goes to 0.91. Here we're even further away, p hat's 0.45, the power is 0.99. So, we'll go back to my nice neat notes. Notice that when p hat is further away, okay, in this case we're talking about a left tail test. When p hat is further away, gets further away, the power gets bigger. If this is what was a right tail test, the power, so if this was on the right side, okay, the further away my p hat is for my alternative hypothesis, the larger the power is going to be. So, here's summarization. What happens when you increase alpha? Alpha goes up, beta goes down, power goes up. What happens when you increase the sample size? Okay, the sample size goes up, the power goes up. What can researchers control to reduce errors? Have a good experiment. Okay, so let me get back to this. So, what I'm saying is, how can, better worded, what can researchers control to reduce power? Okay, to reduce power, okay, they have control over the sample size. So, a larger sample will have a higher power. Okay? They can determine the alpha. Okay? So if they want the power to go up, they can increase the alpha. Okay? We also saw that, probably should add this in as number 4. Power goes up when the alternative hypothesis is far away from the null hypothesis. So another way to control power, which is making a correct decision, is good experimental design practices. You want to reduce extraneous factors, use control blocking stratification, okay, in your experimental design, and reduce any bias that could possibly be taking place when you administer the surveys, non-response, etc. So here, what do you do to maximize power of a test? Sample size. The power increases when the sample size increases. Alpha. Okay? The power increases when you increase alpha. The alternative, okay, that's the alternative hypothesis. Okay? The power is larger as the alternative hypothesis value is more extreme and further away from the null hypothesis. Okay, so here are some good AP test definitions to know. Power is a correct decision. Okay. Power interpretation, you're assuming the population parameter is such. There is a blank probability of finding convincing evidence of the alternative. The power probability statement is that you reject the null hypothesis when the alternative hypothesis is true. We've talked about this. Here are 2 questions that I'd like you to do. These are actual test questions from past multiple choice questions from past tests. Okay, take a moment to read those and do them. And I'll give you the answers in a moment. Actually, you can just pause the video and when you're ready to look at the answers. So for the first question, the correct answer is C. You always select the largest possible sample size and select the largest alpha to increase power. For question 20, the correct answer is A. Noticing that this is a left-tailed test, okay, Here's the alternative hypothesis. It's a left tail test. So you want to select a sample statistic that is as far away from your population parameter as possible. Right? So that's if it were a right tail test, then you would want it to be as large as possible. You want it to be an extreme value.